Hello students, welcome back. So let's continue the lecture in our set, the chapter that we were doing earlier. In the first lecture, we understood how to define a set and what are the different ways of representing a set, that is roster form and set builder form. And we also learned about how to convert a roster form into a set builder form and vice versa. Now in this section, we will be talking about the classification of sets. So the first set of classifications that we will be doing will depend on the number of elements which are there inside the set. So let's continue with the lecture. So the first classification is the empty set. So what sort of sets do we call as an empty set? Let's see with an example. So consider the set where A is set of all the x's, where x is a student of class 11th presently studying in the school. Now, if we have been given this set, we can definitely go to the school and count the number of students presently studying in class 11th, right? So we can clearly see that set A contains a finite number of elements, right? Now let's write another set, which is set B as follows, where set B is all the collection of x's, where x is a student presently studying in both classes 10th and 11th. Now, if you want to identify someone who is simultaneously studying in class 10th and 11th, it is not going to be a possibility, right? Because a single student cannot be present in both the classes at the same time. So we observe that the student cannot study simultaneously in both classes 10th and 11th. So clearly this set is not going to have any element at all. So the set B contains no element at all. Now, once we have an idea that there could be sets where there won't be elements included inside all the time. So those sort of sets is something we call as empty set. And the definition is given as a set which does not contain any element is called an empty set, right? Or it is also termed as null set or void set, right? So all of these represent the same set. So empty set, null set, void set, they all represent that the elements, that means all the three definitions are going to converge on the same conclusion that the set contains zero elements, right? Zero elements. So there are not going to be any elements inside it. All right. Okay, let's see some more examples. Before getting into the examples, we should also understand that how to represent a null set or a void set or an empty set. We usually represent them by symbol phi, or we write it as curly bracket and we do not write anything inside the curly bracket, right? So both of these representations are for empty or null set, right? Let's see some more examples. Consider a set A where it is a collection of x, where x is a natural number and lying between 1 and 2. Since we know that there are no natural numbers which lie between 1 and 2, so clearly this is also going to be an empty set. Similarly, x squared minus 2 is equal to 0 and x is rational. Since we know that the solution for this equation, x squared minus 2 is equal to 0, will give us two values of x, that is x is equal to plus minus root 2, that means plus root 2 and minus root 2. Both of these are irrational quantities. So if we are trying to find a solution of this equation in rational number form, so there won't be any solution, or there won't be any rational number which will satisfy this equation. So clearly, this is also going to be an empty set. Another example is C is a set where it is a collection of x's. X is an even prime number greater than 2. We know that the only even prime number in the entire number set is 2. So other than 2, if you are trying to find a prime number which is greater than 2, that is not going to be a possibility. Again, it is a null set. And similarly, if you want to find a set which is a collection of x's where x square is equal to 4 and x is odd, since we know that x square is equal to 4 is going to give us two values of x is equal to +2 and -2, and both of them are even, right? So there won't be any odd solution for this equation. So again, it is a empty set. So I hope you have understood what exactly a empty, null, or void set is. Going forward, let's talk about finite and infinite set. Just by looking at the name of these two, we are able to understand that in finite set, there will be finite number of elements, and in infinite set, there will be an infinite number of elements, right? So if you see the three, that is empty set, finite set, and infinite set, this classification is mainly based on the number of elements inside that set, right? Okay, let's move forward. So let A, B, and C. If A is a set given as 1, 2, 3, and 5, 1, 2, 3, 4, and 5, clearly there are 5 elements inside it. So you can count the number of elements. And if you are able to count the number of elements, then the set is called to be, or the set is said to be a finite set. Similarly here, A, B, C, D, E, G. So there are 6 elements inside it. So B is also going to be a finite set. So we observe that A contains 5 elements, B contains 6 elements, right? Now, there is another set C given, and C is given as men living presently in different parts of the world. Now, if you see men living presently in different parts of the world, will you be able to count them? I don't think so, right? So we do not know the number of elements in C. We won't be able to precisely identify that how many elements are going to be inside the set C, right? But it is some natural number which may be quite a big number, right? So by the number of elements in set S, we mean that the number of distinct elements in the set, and we denote it by n of S. So if S is a set and we want to denote the number of elements inside it, we denote it by n of S, right? So if n of S, we also actually give a name to this expression. We call it as a cardinal number of the set. Cardinal number of set, or cardinality of set, or cardinality of set, right? Okay. So if ns is a natural number, then S is called a non-empty finite set, right? Non-empty finite set. So even if you are not able to count the number of elements inside it, but you know that the number of elements is going to be a natural number. So if you are able to identify that there is a fixed natural number which is going to be the number of elements in the set, then the set is said to be a non-empty finite set, right? And if you are not able to establish a conclusion that whether the number of elements inside the set is going to be a natural number or not, then we will say that the set is a infinite set, right? Okay, so consider the set of natural numbers, for example. We see the number of elements in this set is not finite, since there are infinite number of natural numbers, right? We say that the set of natural numbers is an infinite set, right? So if you are able to identify that, okay, this set is going to have an infinite number of elements, then we say that the set is infinite. So definition is a set which is empty or consists of a definite number of elements is called finite. So even the empty set is also a finite set, or the set should have a definite number of elements. Then it is called a finite set. Otherwise, the set is called finite. So if these two are not the cases, then the set will be called as infinite set. So consider some examples. Let W be the set of days of the week. So we know that days of a week, there are 7 days in a week. So this is going to be a finite set, right? Let S be the set of solutions of this equation. We know that there are only 2 solutions for this equation, that is +4 and -4. So this is also going to be a finite set. And let G be the set of points on a line. And then we know that there could be infinite number of points on a line. So this is going to be an infinite set, right? So when we represent a set in roster form, we write all the elements of the set within brackets. This is what we have studied earlier. It is not possible to write all the elements of an infinite set within braces because the number of elements of such set is not finite. So we represent some infinite set in roster form by writing a few elements which clearly indicate the structure of the set followed or preceded by followed and then preceded by 3 dots, right? So that means an infinite set, if you want to write in a roster form, you will write a first few elements of the set. And by writing these elements, if you are able to clearly indicate the structure of the set to be followed, right? So if a pattern or a sort of rule is established through which you will be able to identify the next set of elements, so then what we do is we write the first few elements and then followed by 3 dots is how we represent an infinite set in roster form. For example, if this is a set that is written, right? 1, 2, 3, and so on. So here we can clearly identify the pattern. So if we have 1, we are adding 1 to it, then getting 2. We are adding 1 to it, then getting 3. So clearly the next set is going to be added, add 1 to this number 3, we get 4, then 5, then 6. And if you try to understand that this set is nothing but the set of natural numbers. So clearly, just by writing the 3 elements, we are able to establish a pattern and then identify what are the elements that are going to follow here. Similarly, if you write the set, if you try to understand what exactly this set is going to be, so we have 1, 3, 5, and 7. Clearly, we can see that all the odd numbers are listed, odd natural numbers are listed. So this is going to be a set of odd natural numbers. Similarly, if you write this, clearly we can see that we have written all the integers here. So it is going to be the set of integers. So all these sets are infinite, right? Now here we also discussed in our previous class that all infinite sets cannot be described. So this is an important point, that all infinite sets cannot be described in roster form, right? For example, if you take the set of real numbers, this cannot be described in a roster form because the elements of this set do not follow any particular pattern. So if you try to write the set of real numbers in a roster form, you won't be able to do that because the elements inside the set does not follow a particular pattern, right? So this set cannot be written in roster form. So it is not that you can write every infinite set in a roster form. Only those sets can be written in roster form for which the elements follow a particular rule, a particular law, or particular pattern. And through the pattern, you will be able to recognize the other elements which are going to be the members of the set. If you are able to do that, then that set can be written in a roster form. And if not, then the set cannot be written in a roster form. So let's see some examples. So we have to state which of the following sets are finite or infinite, right? So let's see the first set. So first set is a collection of x. X is a natural number and x satisfies this equation. So clearly, if you solve this equation, you are going to get two values of x, that is 1 and 2, right? So only two elements are going to be a member of this set. So this is going to be a finite set. Similarly, x is a natural number and x square is equal to 4. So what are the natural numbers that are going to satisfy this equation? So only x is equal to 2 is going to satisfy this equation. So this set has only one element. So this is also going to be a finite set. Similarly, x is a natural number and 2x minus 1 is equal to 0. Since we know that the solution of this equation is x is equal to 1 upon 2, but it is not a natural number. So this is not a natural number. So this is an empty set. And we know that empty set is also a finite set. So this is also going to be a finite set. X is a natural number and x is prime. We know that there are infinite prime numbers available. So this set is going to be infinite set because there are infinite number of elements inside it. Similarly, x is a natural number and x is odd. There are infinite number of odd numbers available to us. So this set is also going to be an infinite set because the number of elements inside it is infinite, right? Okay. Now let's talk about equal sets. So the previous three classifications that we have done is based on the number of elements inside it. There is one more classification that we do, and that is called a singleton set, right? Singleton set. This is again based on the number of elements inside the set. Singleton set, as the name suggests, have only one element inside it. So this have only one element inside it. So any set which contains only one element, it is going to be called a singleton set. Like for example, this set has only one element, that is x is equal to 2. So this set is also going to be a singleton set, right? All right. Now let's go for equal sets. Now let's see, given two sets A and B, if every element of A is also an element of B, and if every element of B is also an element of A, that means if suppose there are two sets A and B, and all the elements of set A are there inside set B, and all the elements of set B are there inside set A, then the sets A and B are said to be equal. So equality of sets means a very simple thing. Two sets having exactly the same elements are said to be equal, right? So if you want to define it otherwise, so it is going to be two sets A and B are said to be equal if they have exactly the same elements, right? And we write it as A equal to B. Otherwise, the sets are said to be unequal. So if the two sets are going to have the exactly same elements, then the sets will be said to be equal. Otherwise, they'll be said unequal, and it is going to be represented like this, right? So we consider following examples. Let us say if this is an example, so the elements inside set A is 1, 2, 3, and 4, and elements inside B is also 1, 2, 3, and 4. So these two sets are equal. Now let's see the second example. Let A be the set of prime numbers less than 6. So let's try to write the set A. So A is a set of prime numbers less than 6. So prime numbers less than 6 are going to be 2, 3, and 5, correct? Then P is a set of prime factors of 30. P is a set of prime factors of 30. So prime factors of 30 are going to be 2, 3, and 5, correct? And so here we can clearly see that the elements inside set A are exactly the elements inside set P, and vice versa, right? So these two sets are going to be equal. So we can clearly say from here that A is equal to P. Now let's see one note. A set does not change if one or more elements of the set are repeated. We have already seen in our definition of set that set is usually a collection of well-defined unique objects. So if you repeat one of the elements inside the set, it is not going to do any difference, because say for example you have set A written as 1, 2, and 3, and set B you are repeating 2 twice, you are repeating 3 thrice, but the unique elements, if you try to identify, are going to be still 1, 2, and 3, correct? So there is no point in repeating an element. And by repeating an element, the set does not change, right? So a set does not change if one or more elements of the set are repeated. So these two sets are again going to be equal because the unique elements inside the two sets are still equal, right? Since each element of A is in B and vice versa. That is why we generally do not repeat any elements in describing a set, right? Now let's see an example. So find the pair of equal sets, if any, give reasons. So here you have a set A which have only one element 0. Now let's try to understand what is the element inside B going to be. So you want to find a X, and X is given in such a way that it should be greater than 15 and less than 5. So there are no values of X which are simultaneously greater than 50 and less than 5. So clearly B is a null set, right? B is a null set, correct? Similarly, here you are trying to find the value of X which satisfies this relation. So C is a set that is going to have only 5 as an element. Here you are trying to find the solution of x square is equal to 25. So D is a set that is going to have only 5 and minus 5 as your elements, right? Now, E is an integral positive root of this equation. So we have to find the positive root of this equation. So if you try to solve this equation, there are two values of x that is going to be there. One is 5 and other is -3, correct? So since we are only trying to find the integral positive root, so this set is going to have only one element, that is 5, correct? Because -3 is not positive. So now let's see which of the pairs are equal. So A had only one element 0, but none of the set have an element 0 inside it, right? So clearly there is no set that is going to be equal to A. B is a null set, right? B is a null set, but none of the other sets is a null set. Again, there is no set that is going to be equal to B. For C, I can clearly see that C has only one element 5 and D also have only one element 5, right? D also have one element 5. Sorry, E. E have only one element 5. So these two sets are going to be equal. So you have C is equal to E, correct? And then clearly D is not going to be equal to any other set and E is equal to C. So if you have to find the pair of equal sets, there is only one pair which is going to be equal, that is going to be C and E, right? Let's see another example. Which of the following pair of sets are equal? Justify your answer. So let's say the first set is X is a set of letters in alloy and B is the set of letters in loyal. So let's try to find or try to write X and B in roster form. So X is going to be, since you are trying to find the letters which makes the word alloy, so you have A there, you have L there, you have O there, and you have Y there, right? Similarly, if you try to write the set B, B is basically the set of letters in the word loyal. So you have L there, O there, Y there, and A there. Now, if you compare the two sets, L is present in both the ones, A is present in both the ones, O is present in both the ones, and Y is present in both the ones. So I can clearly say that these two sets are going to be equal. So X is equal to B is going to be our conclusion. For the second set, you have A. A is the collection of N, where N is an integer and N square is less than equal to 4. So you have to write the set of all the integers whose square is less than equal to 4. So the integers are going to be -2, -1, 0, 1, and 2. So this is set A, correct? About set B, you have x square minus 3x plus 2 is equal to 0. So the set B is going to have only two elements, that is 1 and 2, correct? So clearly here in set A there are 5 elements, in set B there are only 2 elements, right? So clearly these two sets are not going to be equal. So in this case, I can clearly say that A is not equal to B, correct? Okay. Now once we have this understanding about what is an empty set, what is a finite set, what is an infinite set, what is a singleton set, and what is equal sets. With this understanding, we will try to solve the questions of exercise 1.2. Okay. So the first question is, which of the following are examples of a null set? Set of odd natural numbers divisible by 2. Set of odd natural numbers divisible by 2s. Since the definition of odd numbers itself is that it should not be divisible by 2, right? So obviously, no natural number, no odd natural number is going to be divisible by 2. So this is an empty set, right? Set of even prime numbers. There is a prime number which is even, that is 2. So this is not going to be a null set, right? Then you have, so this is a null set, this is not a null set. In the third one, you want all the collection of x's, where x is a natural number. X is less than 5 and greater than 7. Whenever there is an and in between, that means both the statements have to be true simultaneously. So this one has to be true and this one has to be true at the same time. So you cannot have a natural number which is less than 5 and greater than 7 at the same time, right? So this is again an empty set. So this will be an empty set. Then you have y. Y is a point common to any two parallel lines. So when you have parallel lines, so the definition of parallel lines is itself, it says that the two lines never intersect each other. So when the two lines are not going to be intersecting each other, then they will not be having any common point in between them. So this is also going to be a null set, right? Okay, so the next question is, which of the following sets are finite or infinite? The set of months in a year, since we know that in this set, the number of elements in this set is going to be 12. See, we know that there are 12 months in a year. So if we call this set as E, we know that n of E is 12. So this is going to be a finite set. Here you can clearly see we are writing all the set of natural numbers. And we know that there are infinite number of natural numbers. So this set is going to be an infinite set. Here we can clearly see that the number of elements in set, say we are calling this set as A. So the number of elements in this set is 100, which is a natural number. So this is going to be a finite set. Set of positive integers greater than 100. So if you try to write all the positive integers greater than 100, so you'll have 101, 102, but there will be, that means you are trying to write all the natural numbers which are greater than 100. And again, there are infinite number of natural numbers greater than 100. So clearly, this is also going to be an infinite set. Then the set of prime numbers less than 99. So prime numbers will start from 2, right? And then you have 3, you have 5. And all the prime numbers that you are going to write are going to be less than 99. So the number of elements in set is going to be a finite number, right? It is not going to be an infinite number. So this set is also a finite set, right? Okay, let's see the third question. State whether each of the following set is a finite or infinite. The set of lines which are parallel to x-axis. So if you draw your x and y axis, so this is how the axes are drawn. This is x-axis. There could be infinite number of lines which we can draw parallel to x-axis. So this is an infinite set, right? Set of letters in English alphabet. We know that there are only 26 letters in English alphabet. So this is a finite set. Set of numbers which are multiple of 5. There are infinite number of numbers which are multiple of 5. So this is again going to be an infinite set. Set of animals living on earth. Though we will not be able to count the number of animals living on earth, but we know that whatever their number is going to be, it is going to be a natural number, right? It is still going to be a natural number. So the cardinality of this set is a natural number. So this set is also going to be a finite set. The set of circles passing through the origin. So there could be infinite number of circles which can pass through the origin, like this one, and so on. So again, this is an infinite set, right? Okay. In which of the following, in the following state whether A is equal to B or not. So if we have to find whether A is equal to B or not, we have to see that every element of A should be there in B and vice versa. So if A is here, A is also here. B is here, B is also here. C is here, C is also here. D is here, D is also here. So in this case, you have A is equal to B, right? This one, you have 4, 4, 8, 8, 12. Now 12 is something that is not available in B, right? So these two sets cannot be equal. So A is not equal to B. Similarly, you have 2, 4, 6, 8 and 10. And x is a positive integer and x is positive even integer, right? And less than equal to 10. Positive even integer less than equal to 10 is going to be 2, 4, 6, 8 and 10, right? So these two sets again are going to be equal. So these two sets are equal. A is a multiple of 10 and here you have, so in A, if x, you are collecting all the x's which are multiple of 10, that means all the numbers in set A are going to end with a 0. But here you have numbers ending with 5 as well. So these two sets cannot be equal, right? Let's see the fifth question. Are the following pair of sets equal? Give reasons. So here you have two elements, 2 and 3. So you have to find the two elements inside set B. So equation is x square plus 5x plus 6 is equal to 0. And if you try to solve this equation, you can factorize this as x plus 2 into x plus 3 is equal to 0. So the values of x that are going to be satisfying this equation are minus 2 and minus 3. So clearly here in A, you had 2 and 3 as elements. Here in B, you have minus 2 and minus 3 as elements. So these two sets are not going to be equal, right? Here you have A, which is collection of x's, where x is a letter in the word follow. So if you try to write in roster form, you'll have F as an element, O as an element, L as an element, and W as an element. And similarly for B also, you have W as an element, O as an element, L as an element, and F as an element, right? So W is here, W is here, F is here, F is here, O is here, O is here, L is here, L is here. So these two sets are going to be equal. So in this case, you have A is equal to B, right? Okay. From the sets given below, select equal sets. So all you need is to identify the pair where you have the same elements inside. So here you have 2, 4, 8 and 12. So do you have any other set which have 2, 4, 8 and 12? No. You have 1, 2, 3 and 4. Do you have any other set which have 1, 2, 3 and 4? Yes, this one. So you have B and D are going to be equal. So the solution for this is B is equal to D. Now let's move forward. You have 4, 8, 12 and 14. 4, 8, 12 and 14 is not going to be there in any set. Here you have minus 1 and 1, and here also you have minus 1 and 1. So again, E is equal to G, right? This is also a pair of equal sets. F you have 0 and A, H you have 0 and 1, so obviously these two are not going to be equal. So these are the only two pairs of set which are equal. So in this lecture, we studied about cardinality of the set, and basis the cardinality, how do we classify different types of sets, right? So we studied about empty set, which is also called null set or void set. We studied about finite and infinite set, and we studied about equal sets, right? In the next lecture, we will continue with the remaining topics of the chapter. Okay, so keep studying, keep working hard. We will be, taking all the questions inside the NCERT class 11th. And it will be like line by line, we will be studying NCERT, understanding every aspect of it. And I'll try to explain whenever possible that how exactly things are to be conceived and to be understood, so that you'll be able to recall it properly when you try to solve questions, right? So see you in the next lecture. Till then, have fun, be stress-free, and be confident.